So we've seen in previous videos that if you take an ellipse, shown here black with its two foci, and a point M on its boundary, okay, and you just consider the envelope of lines connecting a generic point PT on the boundary and comprising lines which are perpendicular to this generic point minus this fixed point M. So here's the perpendicular line. So I have a family of such perpendicular lines. You sweep out what's known as the negative pedal curve of this ellipse with respect to point M. And this negative pedal curve is a deltoid. So if I place M over here, you can see that here's the deltoid. And this deltoid has a constant area over all M. So it has constant internal area over all M. The three cusps of this deltoid are shown here as red, green, and blue, and I can label them as P1 prime, P2 prime, and P3 prime. The points on the boundary of the ellipse such that they generate these cusps are known as the preimages. So let me go ahead and draw them. I'm going to represent them as P1, P2, and P3. And what the preimage means is that if you place P on one of these special points, for example, P1, if you place it over here, and you draw a line and you can't quite see it, let me move M around a little bit. Okay, and let me place P on that P1 over there. If you draw this perpendicular line passing through that preimage and perpendicular to P minus M, that line is going to be tangent to the deltoid exactly at its cusp. Okay, so you have these three preimages. These preimages concur, and if you connect the preimages to the corresponding cusps, let me expand this image a bit, you're going to see that they concur at a point, and this point happens to be the center of area of the deltoid. Furthermore, I can draw a circle, if I can find it here. The preimage circle, where would that be? Would that be it? No, that's not it. That be it. That's it. So if I actually connect, if I draw a circle that passes through the three preimages, you find that this circle also contains M, and the center of mass is C2. So this is all pretty neat, and I described some of these properties in another video. So these points are concyclic. What I want to cover here is a related, topic or related phenomenon. Let's move P out of the way. So this is just a construction line that is always tangent to the deltoid. I'm going to remove it. Okay, I'm not going to draw it. So now we're just going to focus on this family of constant area deltoids. Okay, as I vary M, the deltoid moves around, but its area is constant, and the three preimages are also slid around on the ellipse. By the way, the triangle formed by these three preimages has constant area as well, right? So if I move M around, this triangle has constant area. The ellipse is actually its Steiner circumellipse. All right, so let's not talk about this right now. There's really a multitude of phenomena here, and we're assembling them in an up-and-coming paper. Okay, so the phenomenon I want to talk about today is the following. I'm going to consider again a point P on the boundary, and I'm going to connect P to M via a line, and here's a perpendicular line. Now what I want to do is I want to consider a line that is related to this perpendicular here, but is rotated a fixed angle, and I'm going to call this angle theta star. Okay, so I'm rotating this line a fixed angle theta star. Now let's consider the envelope of such lines. Okay, so the construction is clear. As I move P around, the whole system moves around rigidly. Okay, the line going through P perpendicular to P minus M is shown here. It's purple, and this other line here is displaced or rotated about P of T by a fixed angle, and in this case, this angle is, say, let's call it 30 degrees or minus 30 degrees. I guess the direction here is counterclockwise, so minus 30 means make a clockwise rotation of 30 degrees. Now let's go ahead and draw the envelope of these rotated lines. And I'm calling this envelope not delta or uppercase delta as on this one, but delta star. Now what does delta star look like? It also looks like a skewed, it looks like a three-cusp object. It looks like a deltoid, but it looks more skewed than the original delta, right? So if I move, for example, P around, you can see that the pink lines are instantaneously tangent to this derived deltoid, okay? Now, several things are noticed about him. First of all, as I vary M, the area of this deltoid is also constant. The area of this deltoid shown over here, and it's actually shown as a negative value because the order of the vertices with respect to this one is inverted. But you can see here that the area of this deltoid is invariant over M. So I'm going to just animate M so we can focus on the area of the deltoid. It's shown here at minus 30 degrees. Okay, so you can see that this area is invariant. And you can also see here that numerically this area is 3/4 that of the original deltoid. So the area of the original deltoid is shown here, 2.54. The area of the pink derived deltoid with respect to these rotated lines is shown here, 1.9064. And this is actually computed numerically right now. We're still lacking a closed form, which is going to come soon. But the ratio of these two areas at this rotation angle 30 is 3/4. If my rotation angle is 45 degrees, I get another even more skewed kind of a deltoid, and now the ratio of areas is half. Okay, so again, I have an invariant derived deltoid, okay, this pink thing here, and the ratio of areas is 0.5. If I go all the way now to 45, 60 degrees, I get a smaller deltoid and my ratio of areas is 1/4. Now, of course, in the limit, as this guy here approaches 90 degrees, my derived deltoid, so I'm almost at 90 degrees with respect to the original perpendicular line. As I approach 90 degrees, my derived deltoid, delta star, is shrinking to a point. And it actually becomes a point when you're exactly at minus 90 degrees. Why is that? Because now my family of lines is simply the P minus M line, and over all P, this family of lines is rotating about M, trivially. So that deltoid is just stuck at M. That's the sort of stationary center of rotation of this family of pink lines, right? So the phenomenon at play here is that when I don't have a 90-degree angle, for example, let's just pick 60 degrees as we had before, or 30 degrees, okay? I have this family of rotated lines, okay? And they sweep over M, a family of pink constant area deltoids. Okay, so let's observe these over here. Now, notice I'm showing in this animation the center of area of this new deltoid. It's shown here as C star 2. I can also light up the center of area of the original deltoid, C2. Okay, now several things can be observed here. First of all, the preimages of the cusps of the new deltoid coincide with the preimages of the cusps of the original deltoid. Let's see how this works out. I'm going to place P, say near P1, so I'm going to move P near P1 over here. You can see that I'm approaching the tangent of the perpendicular to P minus M to this first cusp here. So and the same thing is happening to this cusp here. So it looks like this cusp is a descendant from this cusp, right? So now let's actually place P exactly on P1. I have a button to do this. And now P is placed exactly on P1. And I can see now that the perpendicular to P minus M goes exactly through the cusp of the original deltoid. And this perpendicular gyrated 30 degrees clockwise goes through this cusp. Okay, of course, if I gyrate the whole system counterclockwise, I get another deltoid. You get kind of like a mirror figure, but you get the same exact situation. You have this preimage P1 of P, and let me actually erase P here. P is just right now located right on P1. The preimage of this cusp is also the preimage of this cusp here of the new deltoid. Okay, so you get that, and you can see here that you're going to get a similar phenomenon of concurrence. So let me connect, and I wonder if I implemented this or not. Did I implement the concurrence of these guys? Apparently not. But what I wanted to show is that if I connect these preimages, oh, maybe I did. Let's see here. C2, evolute. Apparently I did not. Uh, hmm. Okay, so what I wanted to show is a phenomenon that if I connect P3 through these cusps, they're all going to, through each of the cusps, right? So a cusp and its preimage, they're going to concur at C2, much like you get this concurrence phenomenon for C2 of the original deltoid. So we think at this point, and we haven't proven this yet, that because this guy here is also 3-cuspid, okay, it's a 3-cuspoid, so it's probably affinely related to this one here, and they're both affinely related, or they are affine images of the Steiner curve or the Steiner hypocycloid. Okay, now I think there is a final phenomenon here. Oh yes, this one is pretty cool. So let me take out these concurrence lines, and I'm going to draw a circle now that passes through P1, P2, and P3. And let me move this system around a little bit. So if you consider the triangle, right, the triangle formed by the preimages, let's see them here neatly. Okay, so let's just place this in a position so we can see the 3 preimages pretty neatly. So I have a preimage P1 here of this cusp. I have a second one here and a third one here. We know that we can connect these to form a triangle, and this family of triangles is actually also area invariant. So if I move M around, this family of orange triangles is area invariant. But there's something really cool, and its barycenter is stuck and stationary at the center of the ellipse. If I actually draw the circle of this triangle, i.e. a circle passing through its 3 vertices, I'm going to draw this as this orange colored circumcircle. It turns out this circle, not only does it pass through, by definition, the 3 vertices, it also passes through M, okay? And it also passes through the center of area of the original deltoid as well as the center of area of this new deltoid. So let's animate this whole figure over M. You can see now that we have a 6-point circle. So it's passing through the 3 preimages, through the driving point M, and through the 2 centers of area, C2 of the original deltoid and C2 star over here of the new deltoid. So I guess this is all I wanted to show for this video. Please watch the previous Garcia deltoid videos that explain further properties of this just beautiful system. Thank you very much.